So we're in this chapter on lumped capacitance. We talked about, transient conduction. We've talked about lumped capacitance before. We also talked about spatial effects. And now we want to talk about semi-infinite solid. Transient conduction in a semi-infinite solid. You say, I don't know too many applications where it's semi-infinite solid. That would mean that it's like half of the world. I'll have a surface and then the rest of the world. We'll introduce a coordinate system x, and we'll think about the temperature. We'll plot it like on the y-axis. The temperature is a function of position. X goes 0 off to infinity. And we'll think about the temperature initially is everywhere T initial inside my semi-infinite material. But then abruptly, I'll do something at that boundary. I'll either move the temperature to an elevated value, maybe I move it to Ts, so it's higher temperature, and then what's going to happen? Well, there'll be conduction into the semi-infinite solid. And so maybe a millisecond later, the temperature profile looks like this. 10 milliseconds later, 100 milliseconds, 1 second, 1 minute, 1 hour later, you could see that we have now the temperature is propagated. It's heated up deeper and deeper into that semi-infinite solid. That's the first one we're going to solve. And then after we solve that, we have abrupt temperature change at the surface. We're going to look at, don't do that for the boundary condition. Apply a heat flux at that. Well, what's the application of that? Maybe you have a laser and it's impinging some power deposited at that surface. Okay, that's a possible application. Another one is don't just move the temperature, don't apply a heat flux, just expose it to a convecting fluid with a different temperature, T infinity, and a convection coefficient. Where we're going to find that one gives us the most, the longest, most challenging analytic solution, the last case. The middle case, where the heat flux is not as applicable as the first case, which is an abrupt change in the surface temperature. That's the one we're going to look at first. Abrupt change in the surface temperature. So here's the solution to it. What we find is that our temperature profiles, as time increases, they look very, very similar. So what you can do is you can take our governing PDE and transform it into an ODE. PDE, harder. ODE, simpler, easier to solve. Partial differential equation, second order in space, first order in time, challenging. ODE, a little more mathematically abstract because we're going to have a similarity variable, but it will only have 2 conditions, additional conditions, not 3. So here's our PDE. Does it look familiar? Transient heat equation, conduction, we have the capacitance, and so we have 1 over alpha. Hey, I forgot, what was alpha? What is this alpha right here? Thermal diffusivity, right. This is initial condition at time equal to 0 at all position x. That's initial temperature profile. It's just uniform, Ti. This is a boundary condition at x goes off to infinity, kind of far away boundary, right? That it's a Ti and it stays Ti. And this is at x equal to 0. At time greater than 0, you abruptly change it to that surface temperature. So this is initial condition, boundary condition, boundary condition. We introduce a similarity variable. Why? Because these solutions look similar, just stretched a little bit. Somebody else did this long before me, using this similarity variable. It's space as well as time in that similarity variable. Some people will put eta is equal to x divided by 2 square root of alpha t. What's the difference between this definition of eta and this definition of eta? Nothing. Some books will actually define eta as just x divided by the square root of alpha t. What's the difference there? Missing the half. True? So you have to be a little careful whether or not you have the half, or is it the square root of 4, or whatever. You just have to be slightly careful on what is the eta in that textbook that you're using. This is the eta here for this textbook. Well, there's some math. You transform it into an ordinary differential equation. You have two space derivatives or with respect to eta and one space derivative with respect to eta. This eta times dt d eta makes it a little more challenging. Our boundary conditions transform. Notice that this one and this one give us the same, like 3 have to collapse into 2. So the first two, the initial and boundary condition, can collapse into the same condition for the transformed problem in the ODE space. So this is like the first and this is the second. Well, that's well-posed mathematical problem. It's your old friend. The solution is your old friend, another function you haven't seen for a long time. So what is this function? The error function. So the solution gets packaged up into a simple expression, error function. This is the definition of the error function. So if you wanted to, you could unravel and say, hey, here's the temperature. It's a function of the error function. It's equal to Ts plus T initial minus Ts times ERF of x divided by the square root of 4 alpha t. So I've kind of replaced this as t as a function of position and time in there. And there's the temperature profile. That's the solution. It will give you these beautiful curves like this, which look stretched. One, stretch a little bit, or overlay the other previous curve. All right. So if you go ahead and plot, this is the error function. What does it start at x equal to 0? What does it start at? What's the error function at x equal to 0? 0. Okay, at x getting quite large, let's say it's in the vicinity of, 3 or more, what does error function give you back? 1. It looks a lot like the hyperbolic tangent, doesn't it? But it's not, slightly different. And so this is the profile right here. And, well, it gets pretty close to 1. You don't have to go out to 3. You can go to a lot less. If somebody says, I want to get pretty close to 1, but not necessarily all the way to 1, how far out do I need to go? How large does x need to be such that the error function is close to 1? Well, you say, how close is close? How about 0.99? Could you visually see what it might be? Yeah. And so I think I may have that on the next slide. Well, here is in our appendix. We don't have a plot in this textbook. That one I've grabbed off the internet, Wolfram Alpha. But here is, I'm not using x, but w, and it starts 0 and it goes all the way to 3. And you can see it's 0.999. Oh, yeah, that's really, really close to 1. Let's back up. Where is it close to 0.99? You see that? 0.99 is right around here, a little over 1.8. Little over 1.8. It's close enough. So a lot of times in fluid mechanics or in heat transfer, 0.99 is close enough to 1 to say we're there. All right. So if you go out and you say, give me the error function, give me the value of x when the error function is 0.99, it comes back with more digits than you want, but it's close to 1.82, and we'll use that value in a second, 1.82. In fluid mechanics, you talked about the velocity profile. In heat transfer, especially when we get to convection, we're going to talk more about the thermal temperature profile. So if I just turn the problem around this way and plot it a little different, maybe I'll put it as a function of y instead of x, distance out into some semi-infinite medium, where y starts at 0, that's our boundary. And we're going to talk about the temperature. Maybe we put the temperature in this axis, the x-axis. Here is our abrupt change in the surface temperature. Here is our initial temperature of the material. What would the profile look like? It would look like this, and then this, and then this, etc., increasing in time. I just turned the axis a little bit, flipped it a little bit, right? Okay. Well, in fluid mechanics, we were accustomed to plotting things with respect to y, like the velocity profile. Maybe we plotted the x-axis, x-direction velocity. Remember, v as a vector is u I plus vj plus wk. Okay, just u is the x-axis of the velocity. All right. For a similarity between these two, where we're going to talk about a penetration depth into a semi-infinite material or the penetration into a semi-infinite fluid, what I need to do is I need to think about the fluid initially is all at rest. All of the fluid's at rest. And so I'm going to plot u on the x-axis for our velocity, and it's all at rest. And then what I'm going to do is, just like I abruptly change the surface temperature, I'll abruptly change the velocity at y equal to 0. And we'll make it go all the way out to something like u naught, boom, or us. This is an impulsively started plate in a semi-infinite fluid. The bottom plate just all of a sudden was at rest, and now it's boom. It's now moving at constant speed, u naught, to the right. And guess what you get? Velocity profile that penetrates into the semi-infinite fluid. All right, what is our governing differential equation for the penetration of temperature into the semi-infinite solid? It was the equation we just wrote. What was it? It was the second derivative of temperature with respect to space. If you want to put a k over there, that's great. Then you have rho c partial of t with respect to time. We brought that k underneath the rho c, and we said, hey, that's alpha. K over rho c is alpha, so a little shortcut, there it is. 1 over alpha. That's our governing differential equation. What about the fluid mechanics? Well, we had viscosity, true, and that helps accelerate it. And so you had acceleration, so we have the second derivative of u with respect to x squared. If you wanted, you put a mu over there, and then you have a rho, first derivative of u with respect to time. That's our acceleration. If I bring the mu underneath the rho, what do I get? 1 over nu. Mu, nu, very confusing. What is nu? The viscosity. What was the type of viscosity? Absolute or kinematic? Kinematic viscosity. What are the SI units for alpha, and what are the SI units for nu? They're the same. Meters squared per second. So we have very similar differential equations, very similar boundary conditions, and very similar solutions, and we get the same type of eta. Eta is our dimensionless, similarity variable. It's x divided by the square root of 4 alpha t. Over here, eta, similarity variable. You can look in your fluid mechanics book. X divided by the square root of 4 blank t. Everything's the same except for what is fill in the blank. What is fill in the blank for that? It's not alpha, it's nu. It's not thermal diffusivity, it's the kinematic viscosity. And so now you can say, I know the profile, and we know the error function, and so now I can say, how far out, this is classic fluids, how far out is this penetration of my velocity profile felt into that fluid far away from this plate? Normally we have a plate and we would flow the fluid over it, and then we talk about the growth of the boundary layer. Well, here it's impulsively started, and I have a growth of something, penetration depth, like a boundary layer into it. And you'd say, oh, well, this is my penetration depth. It was eta penetration is 1.82. That's equal to x divided by 4 nu t, all that square rooted. And so guess what? This penetration depth, delta v is equal to 1.82. Sometimes we pull the 2 outside, square root of nu t. This 1.82 times 2 is 3.64 square root of nu t. The penetration of the velocity profile into that stationary stagnant fluid when I have an impulsively started plate at the bottom that's the solution. So it grows with respect to time t to the 1/2. It'll grow more rapidly initially and then slow down the rate of growth deeper into the fluid as time marches on. If you plot it, somebody says, I want you to plot the function t to the 1/2 as a function of t. Does it look like this? Does it look like this? Does it look like that? What does it look like? The last one I drew. True? So it grows rapidly and then slows down on the growth. Well, guess what we have over here? We have the penetration, thermal penetration into a semi-infinite material is equal to 3.64 square root of alpha t. A lot of times things don't have to be semi-infinite to do a good job of analyzing what happens in the way of temperature change and heat transfer, approximating it to be a semi-infinite. We can treat our fingers as semi-infinite materials when they're brought into contact with something hot or cold. You can treat a sheet of paper, as thin it is, as semi-infinite if it's rolling very quickly through a machine and being impressed with something hot only for an instant and just flaming through the machines. There's a lot of cases where we can use the semi-infinite approximation or solution for something that's really not semi-infinite. We're just going to be interested in the short time for the temperature change. This brings up another parameter, a Prandtl number. Well, the Prandtl number is defined as nu over alpha. Somebody says, is that a dimensionless parameter? Yeah. Do we have any experience with dimensionless parameters, maybe coming out of fluid mechanics? What other dimensionless parameter dominates the discussion of fluid mechanics? The Reynolds number. All right, the Reynolds number. What's the definition of Reynolds number? Rho, velocity, d over mu. Ta-da. That would be for flow in a pipe and the critical value of 2300 to characterize the difference between laminar and turbulent flow in a pipe. All right, or there's other ones that you can write. You could use length as a scale, right, or u infinity as the velocity. Okay. So how many people not only can remember the grouping, but they can remember what it means? It's used to determine the transition between laminar and turbulent flow, but what is it representing? Something over something, competing forces, competing pressures, competing stresses. What is something in the numerator divided by something in the denominator for the Reynolds number?
That's the ratio of inertial and viscous forces.
A plus. Just give me you just did the final exam. Here's your grade for the whole class, right? A plus. No, that's exactly right. Ratio of inertial to viscous forces. What do I think is probably at least a 50-50 chance that it's on the EIT exam? A question testing the student's knowledge of that concept. I've seen it. I've told students, tell them, go test. You're taking the EIT exam? Good. When you take it, come back and tell me if something like this isn't on it. And the classic question is, the Reynolds number is a ratio of buoyancy to viscous, or inertial to viscous, or static, hydrostatic to dynamic, forces or pressures, something like that. They'll give you a number of options as multiple choice, and guess what? One of them will be the ratio of inertial to viscous, and that's the right answer. Select it. All right? But here we have to think about the Prandtl number. And because we have this impulsively started plate with a semi-infinite fluid above it, or also with the thermal, we have this semi-infinite solid. Now we can do something with this Prandtl number, because if I take the Prandtl number and I do this, if I take and do the square root of that, right? Multiply by t, take the square root, multiply numerator by 3.64, denominator by 3.64. Guess what we just did? What's in the numerator? Penetration into this fluid. It's like a velocity penetration depth. What's the denominator? Thermal penetration depth. So the square root of the Prandtl number is this velocity to thermal penetration depth. How the boundary layer grows in a fluid. Or if you want to do Prandtl number is this delta V divided by delta T squared. True? Yeah. Don't worry too much about the squared. It's how the velocity penetrates. So let's go back to our knife edge plate. Here's our knife edge plate. Typically we have our fluid coming like this. And then we had our growth of the boundary layer. True? This delta V. And it grows into the fluid. Let's say not only do I have no slip conditions, I have a stationary plate and the fluid's coming at it, but I have a hot plate. This plate's now hot. And I have cold fluid. We're going to get to it, but guess what's going to happen? You're going to have a region that of the fluid who's felt the presence of the hot plate and is now starting to be heated. If the Prandtl number is about 1, the growth of the thermal boundary layer will be about the same as the rate of growth of the velocity boundary layer if the Prandtl number is about 1. And we're going to get to it, but air, gases, ideal gases, have a Prandtl number slightly less than 1. Very common. All right. Okay, now let's change it up a little bit, and we're going to say the Prandtl number is not close to 1, but it's much, much less than 1. What's that mean? 0.1, 0.01, 0.001. And then plot the velocity boundary layer as well as the thermal boundary layer. If the Prandtl number is very, very small, look at this, then isn't delta V here equal to the square root of the Prandtl number times delta T? If this is very, very small, if the Prandtl number is very, very small, wouldn't the thermal boundary layer be large compared to the velocity boundary layer? Wouldn't the penetration of the thermal change go faster and deeper than the velocity change? That's true. And then guess what? You can have materials where the Prandtl number is not just, it's just opposite. So what happens there? Knife edge plate. How does the velocity profile grow? Delta V. How does a thermal grow? Delta T. This is a good time to introduce the Prandtl number and hopefully give you a physical sense of it. Okay? Now, once I have the temperature profile, I can be interested very much in the heat flux at the surface. Still, we're only doing this temperature at the surface is abruptly changed to a constant value. And you would say, well, is this the basic equation for the heat flux at the surface? Where did this equation come from? Fourier's law, that's all it is. And so you say, here's our general solution of the temperature profile using our similarity variable. I'm going to have to take the space derivative and evaluate the dt dx at x equal to 0. Well, I'll have to do a little chain rule. You can apply it using that definition. You come out and you work out the math, and there's a very simple relationship for the surface heat flux. So you can see that it's also it rapidly grows, it then slowly curtails because it's proportional to 1 over the square root of time. That's proportional to that. All right. Is that a pi? Yeah, that's a pi there. Temperature difference and then the thermal conductivity. All right. Let's move on. You take your hands out of your pockets or wherever they're at, and you get them up to your body temperature. They won't be the same temperature as the core body temperature, but a lot of times our extremities, like our fingers, are cool compared to the brain temperature or under the tongue temperature when you went to the doctor. What's our internal core temperature? They shoot the little IR thermometer in the ear of the child. What are they trying to get? The temperature to see if they're running a fever. What's our typical internal core temperature? Yeah, 98.67, something like that, degrees F. And your temperature, your fingers are a little less. But if you put them, under your armpit and hold them there for a while, or you put them deep in your pockets or whatever, you get them up to that temperature. Now, rub them together, get them up to that temperature, and do this thought experiment. And then I'm going to start on the clickers and all that. And tell me, when you touch a few things, touch the metal, Pull it away, get your temperature back up. So now it's another test. Touch a piece of wood, touch a piece of paper, touch the plastic, touch the carpet, and tell me, you're going to sense cold or hot. You're going to feel, and then you're going to answer this question, which object feels the coldest? So we'll do this by the old show of hands. Who thinks that the metal feels the coldest? Anybody for wood? Anybody for plastic? Anybody for carpet? No, it's the metal. How does this class explain why it feels the coldest? Let me ask this. Which one has a different temperature? What's the air temperature in this room? 72. What's the plastic chair's temperature in this room? 72. What's the metal support, the desk in this room? 72. All of them have the same temperature. Why does the metal feel cold? It's not only the thermal conductivity, but it's a conductivity plus the other properties which give you that transient. It's a transient effect. If you hold your fingers on the piece of metal for more than a few seconds, it doesn't feel so cold, does it? It has to, the thermal, it has to bring down the temperature at the parts of your finger which are close to the skin, in the skin, so that you can actually sense it and read it in your brain. So it has to penetrate a little bit into your finger, but it will bring the temperature when you touch the metal of your fingers, that interface, closer to the metal temperature, lower. It'll be lowered closer to 72 than if you touch carpet. The carpet temperature interface will be closer to your finger's internal temperature. So what we have is the application of two semi-infinite solids. Finger, which is warmer, object A, and then you have something else, piece of metal, plastic, wood, object B, lower temperature, that's initial. And you introduce a small control volume at that interface. If it's so small, so thin a control volume, it has no thermal inertia. Hence, what comes in goes out of that control volume at every instant in time. This is where most students would say, I don't understand that. This energy balance for a very thin control volume. What's in has to come out at every instant in time. So what comes out of A goes into B. The way we drawn it, A is warmer. What is our equation for the heat flux coming out of A? Well, it depends on that surface temperature. We had A will jump to a surface. The surface temperature could be close to the value of the temperature of A initial. Or the surface temperature could be down here, closer to the B initial. We're going to solve for the surface temperature. That's what really is different. When you touch the metal, that interface surface temperature is lower because of the thermal properties of the metal compared to the other properties of wood and carpet that you touch. And then this is the same equation applied for what flows out into B. We have the thermal conductivity A, thermal conductivity B. So conductivity is very, very important, but it's not the only thing because we also have the thermal diffusivity of those two materials. So you just do a little rearranging, and there's the equation for the surface temperature. And you can read this equation. This is the fraction multiplying A initial, and this is the fraction multiplying B initial. It's just a weighted fraction of those two temperatures. It's going to be between them. Look, at the interface temperature isn't going to be above the highest or below the lowest temperature of the two, right? It's going to be in between. It's just a fraction. So it'll be either like 99 and 1%, or it'll be 90-10 or 50-50 or 10-90, whatever those two fractions come. Property of interest is the K times the rho times the C. Good conductor, high K, high mass density, high specific heat, that leads to a large K rho C, hence it's going to be pulled closer to that object's temperature. All right. There's plenty of applications of this in your everyday life. Can you think of any? How many people have seen this movie? And I'm going to see if this will play.
You're full of beans and so's your old man. Oh, yeah? for the throat.
All right, all right. Come on, Karen. Well, go on, smartass, and do it. I'm going.
Flick's spine stiffened, his lips curled in a defiant sneer. There was no going back now.
This is nuts. Stop, stop, stop!
I know that all his friends are going to leave him now. Now, we move back into the chapter. We did this, case 1, with a constant surface abruptly changing. It's very applicable, and it's a very compact little solution. Now, this is less applicable when you have a heat flux specified, and guess what you get? You get the ERF, the complementary error function, and it's a little more, it's just 1 minus the error function. It's described in the textbook, but it's a little longer solution. And then the most complex, is probably the most common, is when you have a convective boundary condition. There it is. All right, let's solve this problem. We have a thick slab, and they give us the thermal diffusivity. Alpha is 6 times 10 to the minus 6 meters squared per second. And you have a thermal conductivity given of 19 watts per meter degree C. And initial uniform temperature of 75 degrees C. When you see thick slab in this chapter, we already did finite slab. Now we have thick slab. You want the semi-infinite. That's going to be the key word for the semi-infinite solution. Initially, it's exposed to a fluid. When you see the fluid, you have to worry about that third case. That third case where you have the T infinity of 20 degrees C and the convection coefficient of 110 watts per meter squared degree C. Determine the temperature at a depth when the depth x is equal to 0.050 meter and a time of 200 seconds. You go back, you say, I need to be able to evaluate this group of parameters. What does that look like? X divided by 2 square root of alpha t. Our similarity variable, eta. That's what that is. You also have this parameter, h times the square root of alpha t divided by k. That square root of alpha t sure does look like a characteristic length. That looks like a BO number. All right. But you have to compute these, then use the complementary error function and exponential, etc. And you can then go ahead and make a calculation. The eta for this problem comes in at 0.722. The h square root of alpha t divided by k comes in at 0.20. And you could use the analytic equation. You could also use, in our textbook, plots like this. So here is our similarity variable. Here is that modified BO number. You come in about 0.7, a little over, 0.72. Come up to where this 0.2, read across. Get this as 0.04. It should match the analytic if you plug them all in, use the complementary error function, and then unravel, and then you calculate that final temperature. T is equal to 0.04 times T infinity minus Ti plus Ti. We covered a lot of material. Let me go ahead and shut this down and we'll start the quiz. Thank you very much.